Imagine our universe. I mean, really picture all its billions of galaxies, trillions of stars, planets, nebulae, everything. And even you.
Mm-hmm.
Every single atom that makes you up. Now imagine all of that compressed, squeezed down into an infinitely small, infinitely hot, infinitely dense point.
Right. The classic image of the Big Bang's starting point.
Exactly. That's the Big Bang, the cornerstone, really, of our cosmic story. The moment our universe just burst into existence.
It explains so much.
It really does. But, for all its power, there's this absolute colossal question just hanging over it.
Which is,
What was there before that moment? What came before the beginning?
oh, yes, the big one.
And it's not some, fringe idea anymore, is it? It's genuinely one of the most challenging, most exciting questions in all of physics.
Absolutely. It pushes us right to the edge of what we know, maybe even what we can know.
It demands we rethink everything, maybe even time itself.
Precisely.
So today, we're doing a proper deep dive. We're going right to the absolute edge of cosmic time.
To the beginning and maybe before.
Our mission, really, is to try and unpack this incredible puzzle of the universe's origins. We want to explore some of the groundbreaking theories, some of them pretty abstract, let's be honest,
Oh, definitely mind-bending.
to try to answer that question. What came before the Big Bang?
Mm.
So get ready, because we're about to venture into realms where, well, the known laws of physics kind of meet their match.
Where our usual tools start to fail us.
Yeah, and where your sense of reality might just get stretched a little bit thin.
It's a really profound area to explore because, our most successful theory for describing the universe on the grandest scales, that's Einstein's general relativity.
Right. Gravity is space-time curvature.
Exactly. That theory actually hits a wall, a conceptual impasse, right at that initial moment.
The singularity.
The singularity,
Yeah.
yeah. It predicts this state where its own equations just break down. They give infinite answers, which is usually a sign that the theory is incomplete.
So just asking the question, what was before,
Mm-hmm.
forces us to go beyond Einstein.
It compels us, really. We have to journey into territory where physics, as we know it, needs a radical new understanding. Ideally, we need that theory you hear about quantum gravity.
The unification of the big and the small.
That's the dream. So this deep dive, it isn't just about, listing facts. It's about pushing the absolute limits of human thought.
Exploring ideas that might redefine existence itself.
Yeah, offering not just answers maybe, but definitely profound new questions.
That really is the challenge, isn't it? The absolute frontier. Okay, so here's the roadmap for you today. First, we'll dig into why this question is so incredibly tough. Why can't we just, look back further?
The limits of our current physics.
Then we'll look at the clues. What hints does the universe give us from right after the beginning?
The echoes of creation, basically.
Exactly. And then we get to the really wild stuff. We'll explore some visionary, but still scientifically grounded ideas about what might have come before.
Things like bouncing universes.
Colliding dimensions.
Universes spawning other universes.
Or maybe even a universe that didn't really have a beginning in the way we think about it.
It gets pretty strange.
Prepare for some genuine aha moments, or maybe some wait, what moments, because this is where the universe truly gets wonderfully weird. Okay, first section then. The cosmic curtain call. Why before is such a hard question. Let's unpack this core difficulty.
Right.
Our understanding of the big picture universe, planets, stars, galaxies, clusters of galaxies, all of it, it's described magnificently by Einstein's general relativity.
It's an incredibly successful theory.
Beautifully elegant, too. It completely changed how we see gravity, not a force pulling things, but the actual shape, the curvature of space-time itself.
Yeah.
That four-dimensional fabric weaving space and time together.
And it's been tested again and again, bending starlight, the orbits of planets like Mercury.
Even detecting gravitational waves from colliding black holes, right? Stunning confirmation.
Absolutely. It's a titan of modern physics, a real testament to human insight.
So we have this powerful theory. How does it lead us to the Big Bang, and why does that become a problem?
Well, you take general relativity and you combine it with a key observation. The universe is expanding.
Galaxies are moving away from us and from each other. Edwin Hubble's discovery.
Exactly. So if things are expanding now, logically, if you run the clock backward,
Everything must have been closer together in the past.
closer, denser, and hotter, much, much hotter. Keep running that clock back, and general relativity points inescapably towards an origin.
The Big Bang.
The Big Bang model, yes. A universe starting from this unimaginably hot, dense state about what, 13.8 billion years ago?
And like we said, this isn't just a guess. It works brilliantly. It explains the cosmic microwave background.
The CMB, yeah, that faint afterglow of the initial fireball. Essential evidence.
It predicts how much hydrogen and helium should have been created in the early universe.
The light element abundances, yep, matches observations remarkably well.
And it even explains the large-scale structure we see today. Galaxies arranged in filaments and voids. How that grew from tiny initial seeds.
It's a remarkably successful framework.
What? When you push it right back to time zero, to the absolute instant of creation.
That's where the trouble starts. That's where you hit the singularity.
Right.
Precisely. The problem is that general relativity, when you push it all the way back to time zero, predicts that the entire observable universe, everything we can see now, stretched across billions of light years, was concentrated.
Into what?
Into an infinitesimally small point. A point with infinite density, infinite temperature, and infinite space-time curvature.
Infinite.
That's the prediction. We call it the initial singularity.
Okay, infinite sounds impressive, maybe? But in physics, that's usually bad news, right?
A huge red flag, yeah. A singularity isn't really a physical thing you can point to. It's a mathematical point where the equations of the theory just stop making sense.
Like trying to divide by zero.
Exactly like dividing by zero. The answer is undefined. The very language we use, the mathematical tools of general relativity, they just break down. Kaput.
So it's a limit on our theory, not necessarily a description of reality at that point.
That's how most physicists view it, yes. It signals that general relativity is incomplete under those extreme conditions. We need something more fundamental.
Which leads to the critical point. If the laws, the equations, break down,
then we simply cannot use general relativity to describe what the singularity is. We can't say anything meaningful about its properties using that framework.
And crucially,
we can't use it to predict what emerged from it or what might have existed before it.
it's like a wall.
It effectively becomes a wall in our understanding, yeah. A conceptual barrier. We can describe the universe fractions of a second after this supposed point, but not the point itself, nor anything leading up to it. We're essentially blind before that moment, according to standard GR.
And the conceptual weirdness just keeps piling up, doesn't it?
Oh, it gets deeper.
Because the standard Big Bang model, based on GR, doesn't just say matter and energy began at the singularity.
No, it suggests space-time itself began then.
Time and space, the very stage on which everything happens, are fundamental coordinates. They supposedly emerged right then.
That's the implication within that standard framework. Time and space are properties of the universe, and they came into being with the universe.
So if you accept that, asking what came before the beginning of time,
it becomes conceptually paradoxical, almost nonsensical within that specific model.
like asking what's north of the North Pole.
Exactly that analogy. Before implies a sequence, a timeline. If time itself hadn't started yet, the concept of before loses its meaning.
Which is why we can't just, build a better telescope to see before the Big Bang.
Precisely. It's not a limitation of observation in that sense. It's a fundamental theoretical barrier within general relativity. Moving beyond it demands a new physical theory.
Something that can handle both gravity and the quantum world.
Exactly. A theory of quantum gravity.
Right.
One that can describe the universe at those unbelievable energies and densities without breaking down, without hitting infinities.
And we don't have that final complete theory yet.
Not yet. We have promising candidates like string theory, loop quantum gravity.
Which we'll get into.
Right, but no definitive, experimentally confirmed theory, which means all the answers we're about to discuss, all these ideas about before the Big Bang,
They're speculations.
they're fascinating, highly informed, mathematically rigorous speculations. They represent the absolute cutting edge where brilliant people are trying to build the theoretical tools needed to see beyond that cosmic curtain.
Okay, so we can't directly look before the singularity using our current physics, but we're not completely in the dark, are we? We can look at the immediate aftermath.
Absolutely. And that aftermath gives us crucial clues, like cosmic fingerprints left behind from those very early moments.
Clues that any valid pre-Big Bang theory would need to explain or be consistent with.
Precisely. And the most important piece of evidence, really the cornerstone of observational cosmology, is the cosmic microwave background, the CMB.
Right, you mentioned it earlier, the afterglow.
Exactly. It's this faint, incredibly uniform glow of microwave radiation. It's literally everywhere, filling the entire universe, coming at us from every single direction we look.
It's not coming from stars or galaxies.
No, it's much older than that. It is the residual heat left over from when the universe was incredibly hot and dense, a time before stars even existed.
How old was the universe then?
Only about 380,000 years old, a mere baby in cosmic terms. Before that, it was so hot and dense that it was opaque light couldn't travel freely. The CMB is the light released when it finally cooled enough to become transparent.
So it's like a photograph of the infant universe.
A perfect analogy. It's a snapshot of the universe at 380,000 years.
Yeah.
And its existence, its temperature, its tiny variations,
Yeah.
they are powerful proof that the universe did start in a hot, dense state and expanded, just like the Big Bang Theory predicts.
Okay, so the CMB is proof of the hot, dense start. But you said it also presented a puzzle.
A major one, yes. It's remarkable uniformity.
Uniformity, meaning it's the same temperature everywhere.
Incredibly close to the same temperature, yeah. About 2.7 Kelvin everywhere we look across the sky. The variations are tiny, like 1 part in 100,000.
So what's the puzzle? Shouldn't it be uniform if it all started together?
But think about the scale. By the time the CMD was released, the universe was already vast. Regions on opposite sides of the sky that we see today were back then incredibly far apart.
Too far apart for light to have traveled between them.
Exactly. According to the standard expansion model without inflation, these regions were outside each other's causal horizon. They couldn't have exchanged heat or information. They couldn't have communicated to agree on the same temperature.
So how did they end up at the exact same temperature? It's like finding two strangers on opposite ends of the Earth who somehow coordinated to wear the exact same very specific outfit without ever talking.
That's a great way to put it. It's highly improbable. This is the horizon problem. How did causally disconnected regions reach thermal equilibrium? And to solve this puzzle, along with a couple of others like the flatness problem.
Which is about why the universe's geometry seems so perfectly flat.
Yes. To solve these, cosmologists developed the theory of cosmic inflation.
Inflation. Okay, this is a big one. What is it?
It's the idea that in the very, very first fraction of a second after the Big Bang, we're talking an almost unimaginably tiny sliver of time, like from 10 to the minus 36 seconds to maybe 10 to the minus 32 seconds.
Wow. Okay.
The universe underwent a period of absolutely hyper-accelerated exponential expansion.
Faster than the speed of light.
The space itself expanded faster than light could travel across it. The universe ballooned in size by an incredible factor, maybe 10 to the power of 26, or even much, much more. Just poof.
Okay, that's hard to picture. What did that do?
Well, imagine a tiny region just before inflation starts. It is small enough to have reached thermal equilibrium, the same temperature throughout. Then, inflation kicks in and stretches that tiny uniform patch to become enormous, essentially becoming our entire observable universe.
So the regions we see on opposite sides of the sky were in contact before inflation stretched them apart.
Precisely. Inflation solves the horizon problem by saying these regions were close enough to interact and homogenize before this rapid expansion flung them far apart. It also flattens out any initial curvature, solving the flatness problem.
So inflation happens right after the initial moment, but before the CMB is released.
Correct. It's a crucial step in the very early universe, bridging the gap between the presumed beginning and the later phases we understand better.
And while it doesn't directly solve the singularity problem itself.
No, it generally assumes some sort of beginning point from which inflation starts, but it does provide a vital context. It sets the stage, you could say.
Yeah, it creates the conditions, the large, smooth, flat universe that subsequent evolution and potentially these pre-Big Bang theories need to account for. It gives us a slightly less opaque window into those absolute earliest moments.
Exactly. It's a key part of the modern cosmological picture, and many pre-Big Bang ideas are formulated within or connected to the inflationary paradigm.
Okay, so we've established the problem, the singularity, and a key piece of the early universe story, inflation. Now let's get into the theories trying to peek behind that curtain. What came before?
Right, and one of the most maybe intuitive ideas, one with really deep historical roots, actually.
Like ancient philosophy, even.
Yeah, you find echoes of it in Hindu cosmology, some Greek thought. The idea that our universe isn't a one-off event.
But part of a cycle?
Exactly, an endless series of cosmic cycles. Birth, expansion, maybe contraction, and rebirth. It feels almost natural, doesn't it? Like the universe breathing in and out.
So expansion, then collapse, then another bang?
The classical version, yes, involves something called the Big Crunch. The idea was that gravity eventually would overcome the expansion.
Pull everything back together.
Right. All matter collapses back down, leading to another final singularity which could then somehow trigger the next Big Bang.
But that still has the singularity problem, just at both ends.
It potentially does, yes.
Hmm.
Which is why modern cyclic theories try to go further. They incorporate quantum physics to try and avoid the singularity altogether.
Okay, how do they do that? This is where it gets really fascinating, right?
Yeah.
Where quantum mechanics might offer a way out of Einstein's infinities.
Exactly. Modern cyclic theories, especially those inspired by a framework called loop quantum gravity, or LQG.
Loop quantum gravity. Okay, what's the key idea there?
LQG is one of the main approaches trying to merge general relativity and quantum mechanics. Its core idea is that space-time itself isn't smooth and continuous like we usually imagine.
It's not like a rubber sheet.
Not at the most fundamental level, no. LQG suggests space-time is quantized. It's made of discrete chunks, or atoms, or fundamental loops of space. There's a smallest possible area, a smallest possible volume.
Like pixels on a screen. Space has a resolution limit.
That's a decent analogy, yeah. You can't zoom in infinitely. Now think what happens if a universe collapses within this framework.
If space is grainy, can it actually collapse to an infinitely small point?
LQG predicts it cannot. There's a maximum possible density, a quantum limit determined by this fundamental granularity of space itself. You simply cannot crush matter smaller than the atoms of space allow.
So instead of a singularity,
You get a bounce. As the universe collapses and reaches this maximum quantum density, incredibly strong repulsive forces inherent in this quantum geometry kick in.
quantum pressure, sort of.
Kind of, yeah. A repulsive force arising from the quantum nature of space-time itself. This force overwhelms gravity at that tiny scale, causing the universe to rebound.
It bounces back outwards.
It bounces, yes, and begins a new phase of expansion.
Which is our Big Bang.
That's the idea of the Big Bounce. Our Big Bang wasn't the absolute beginning, but the result of a previous universe collapsing and bouncing.
So in this view, before the Big Bang was just the previous universe
Yeah.
contracting.
Exactly. A prior contracting phase heading towards its own quantum-limited crunch, which then smoothly transitioned via the bounce into our expanding phase. The timeline could stretch back infinitely, potentially, through endless cycles of expansion and contraction. No singularity needed. Now, there's another related but distinct idea for a cyclic universe coming from a different branch of theoretical physics, string theory, or more specifically, M theory.
Okay, string theory. Tiny vibrating strings instead of point particles.
Right. And M theory is a more encompassing version that includes higher dimensional objects called branes, short for membranes.
Branes, okay.
And this leads to the ekpyrotic universe model. It proposes that our entire universe, all three spatial dimensions we experience, is actually just one of these branes, a vast, perhaps infinite membrane existing within a larger, higher dimensional space.
Higher dimensions. Like a fourth spatial dimension. Or more.
Potentially many more, yeah. This higher dimensional space is often called the bulk. So picture our universe as just a sheet, a brane, floating in this bulk.
But I'm picturing it, a giant cosmic sheet. So where does the Big Bang come from in this picture? It's not a bounce.
No. In the ekpyrotic model, the Big Bang is triggered by a collision.
A collision.
Between what?
Between our brane and another parallel brane, also floating in the bulk.
Whoa! Two parallel universes crashing into each other.
Sort of, yeah. Imagine these two immense, perhaps initially cold and nearly empty, branes slowly drifting towards each other through the bulk dimension. When they collide,
Yay.
Bang! The immense kinetic energy of their collision is converted into the matter and radiation that fills our universe, heating our brane up incredibly and causing it to expand rapidly. That's the event we perceive as the Big Bang.
And this happens periodically. That's the cyclic part of the model, yes. The branes could potentially collide, bounce apart, slowly drift back together over cosmic timescales, and collide again, leading to an endless cycle of cosmic renewal.
And the key advantage here, like the bounce, is no singularity.
Exactly. The universe on our brane never collapses to infinite density. The hot, dense state is generated by the collision energy itself. So before the Big Bang in this model has a clear physical description, it was the state of two cold, nearly empty branes approaching each other in a higher dimension. Again, it pushes the question of the ultimate origin back, perhaps to the origin of the branes and the bulk itself.
Okay, the ekpyrotic model with colliding branes. That's really captivating stuff. You said it's part of a broader idea.
Yes, it's a specific example of a wider framework called Brane Cosmology, or sometimes brane world scenarios. These ideas are all deeply rooted in string theory and M theory.
Which, just to remind ourselves, suggests fundamental reality is made of tiny vibrating strings. And these can form larger membrane-like structures, the branes.
Correct. And Brane Cosmology explores the possibility that our familiar three spatial dimensions are confined to one such brain.
We're stuck on the membrane.
In many models, yes. Matter and light might be confined to the brain, while gravity could potentially propagate through the extra dimensions, the bulk.
Like characters drawn on a sheet of paper can only move in 2D, but the sound of tapping the paper, maybe analogous to gravity, travels through the 3D room.
That's a pretty good analogy, yeah. We're living on the brain, embedded within this larger, higher dimensional reality, the bulk. And there could be other brains, other parallel universes floating nearby in the bulk, potentially undetectable except maybe through gravity.
Mind-bending. Okay, so this whole framework offers a radical alternative to the standard Big Bang singularity,
Absolutely, instead of everything erupting from one infinitely dense point.
which we establish is where our physics breaks down.
Right. Instead, the energy and matter of our universe could have been generated by this grander event, the collision of two pre-existing brains. It's a very different starting mechanism. Imagine it again. Two vast parallel universes, these brains, drifting through the higher dimensional bulk. They might be cold, mostly empty, quiescent for eons.
Just chilling in the bulk.
Pretty much. But then they approach each other, maybe pulled together by some force acting between them or just drifting, and they collide.
And that collision energy.
Gets converted instantly into the particles, the radiation, the heat, everything we see in our universe's hot, dense beginning. This energetic impact ignites our brain, triggering the expansion we call the Big Bang.
It's like striking a cosmic match.
A very, very big match, yes.
Right.
Smashing two universes together to create the energy needed for one.
And the huge advantage, again, is avoiding that singularity problem that plagues standard cosmology.
Completely avoids it in many versions, yes. Because the state before the Big Bang isn't some mathematical breakdown point. It's a physically describable scenario.
Was it again?
It was simply the existence of these two separate, maybe cold, maybe largely empty universes, these brains, moving towards each other through the bulk.
So the question of the beginning of time kind of devolves.
It shifts, definitely. It's replaced by the question of where the brains came from, what the bulk is like, what governs their motion. It shifts the boundary of our ignorance, you could say, rather than hitting that hard wall of the singularity.
Is there any way to test this? Any observable consequence?
Potentially, yes. These brain collision models, especially the ekpyrotic variants, might predict a different pattern of primordial gravitational waves compared to standard inflation.
Gravitational waves from the Big Bang itself.
From the very, very beginning, yeah. Future, more sensitive gravitational wave detectors or perhaps detailed analysis of the CMB polarization might, just might, be able to distinguish between these scenarios. It's a long shot, but it's potentially testable.
Okay, let's switch gears a bit. Remember cosmic inflation, that burst of hyperexpansion right after the Big Bang.
The theory that solves the horizon and flatness problems, yes.
Well, what if inflation didn't just happen once and then stop?
Now you're heading into eternal inflation.
Eternal inflation. So inflation is still happening somewhere.
In many models, yes. Eternal inflation proposes that on the very largest scales, the fabric of space-time is always undergoing this hyper-accelerated expansion. It's not a one-time event. It's the background state of reality constantly creating new space.
So it never actually stopped globally.
That's the idea. It's like a runaway process. Inflation creates more inflating space faster than it can decay into normal space, so globally it just keeps going forever.
Okay, if inflation is always happening out there, how did our universe, the one we live in, come about? We're clearly not inflating exponentially right now.
Good question. The idea is that inflation can stop, but only locally.
Locally, how?
Due to quantum fluctuations. Think of the inflating spacetime as a sort of high-energy field. Quantum effects can cause random, small patches of this field to spontaneously drop to a lower energy state.
Like a ball rolling down a hill and settling in a valley.
Exactly. And when a patch drops to this lower energy state, inflation stops in that region.
And what happens in that region where inflation stops?
A bubble universe is born. That pocket of space, no longer inflating exponentially, undergoes its own more conventional Big Bang. The energy from the inflationary field gets converted into matter and radiation, creating a hot, expanding universe like ours within that bubble.
So our universe is just one bubble.
One bubble that formed within this vast, eternally inflating metaverse or background spacetime.
I think I need that analogy again, the boiling water one.
Right. Imagine a huge pot of water that's eternally boiling. The vigorously boiling water itself represents the eternally inflating parent spacetime, always churning, always expanding.
Okay.
Now, occasionally, a bubble of steam forms within the water, detaches, and expands.
That bubble is our universe.
That bubble is our universe, yes. It formed, inflation stopped inside it, it cooled, expanded like a conventional Big Bang, and started forming stars and galaxies.
But crucially,
While our bubble of steam goes its own way, the rest of the water in the pot just keeps boiling.
constantly forming new bubbles.
Constantly forming new bubbles, yes. Each one potentially another universe, nucleating randomly within the inflating sea. An endless process. So, in this eternal inflation picture, what was before our Big Bang?
It wasn't a singularity.
No,
Yeah.
it was simply the existence of this vast, eternally inflating parent spacetime. Our beginning was just the moment inflation happened to stop in our particular cosmic patch, allowing our bubble universe to form and start its own expansion.
It wasn't the beginning, just a beginning, our local beginning.
Exactly. And this leads directly, almost inevitably, to one of the most profound and, frankly, controversial ideas in modern physics.
Multiverse.
The multiverse. An infinite ocean, potentially, of these pocket universes, constantly butting off from the eternally inflating background.
And these other universes, these other bubbles, could they be different from ours?
Very likely, yes. The way inflation ends. The specific values of the fundamental constants of nature, the types of particles that exist these, could vary randomly from bubble to bubble due to quantum effects during their formation.
So infinite universes, potentially with totally different laws of physics.
That's the staggering implication. An endless cosmic ensemble. Our universe, with its specific properties that allow for stars, planets, and us, might just be one lucky bubble among an infinite number where the conditions happen to be right.
That certainly changes your perspective on our place in the cosmos.
It absolutely does. It offers a potential explanation for why our universe seems so finely tuned for life if you have infinitely many universes. Some are bound to look like ours just by chance, but it's a deeply untestable idea, at least currently.
Okay, we've had bounces, collisions, and bubbles. What's left? Is there anything even more abstract?
Oh, yes. For perhaps the most philosophically challenging idea, we turn to quantum cosmology, and specifically the work of Stephen Hawking and James Hartle.
Hawking and Hartle, their no-boundary proposal.
Exactly. This approach tries to describe the origin of the entire universe using the principles of quantum mechanics from the get-go. It uses a technique called the sum over histories, or path integral formulation.
Which is about considering all possible ways something could happen.
In essence, yes. Instead of a single starting point and trajectory, you sum up the probabilities of all possible space-time geometries that could lead to the universe we see now. And the key proposal they made was that the sum could be calculated without needing to specify any starting point or initial edge or boundary condition for the universe.
No boundary, no beginning edge. How does that work?
Well, this is where it gets particularly mind-bending. They introduced the concept of imaginary time.
Imaginary time, like using the imaginary number I, the square root of -1.
Exactly that. Mathematically, if you treat the time coordinate in the equations describing the universe's geometry as an imaginary number rather than a real number, something remarkable happens near the beginning.
What happens?
The distinction between time and space essentially dissolves. Time, in this mathematical description, behaves just like another dimension of space. It loses its unique, time-like character, its inherent directionality.
So near the Big Bang, time becomes space-like. You can move back and forth in it, like moving left or right.
In this mathematical framework, yes. Think about the surface of sphere, like the Earth. It's finite in area, but it has no edge, no boundary. You can travel all over it, but you never fall off an edge.
Okay.
The no-boundary proposal suggests the space-time geometry of the very early universe is similar. It's finite, but smoothly curved and closed off like the surface of a sphere when described using this imaginary time. There's no sharp starting point, no singularity, no edge.
So back to the North Pole analogy. You can travel north on Earth, but once you reach the North Pole,
There's no north anymore. All directions are south. The pole is a special point on the surface, but it's not a boundary where the surface ends.
and the Big Bang is like the North Pole of time.
That's precisely the analogy Hawking used. In the no-boundary proposal, the Big Bang is the point from which the universe began its expansion in real time. the time we experience. But it's not an edge or a boundary where time itself began from nothingness.
It's just a smooth point on this combined four-dimensional space-time surface when you include imaginary time near the start.
Exactly. The universe is seen as a self-contained quantum system, smoothly emerging without a singular origin or boundary.
So this model doesn't answer what came before by giving us a prior state.
No, it subtly dissolves the question. By proposing that time, as we normally understand it, with a definite past, present, future flow, didn't exist in that primordial quantum state. There was no before in the conventional sense because there was no conventional time yet.
It redefines the whole concept of a beginning.
It's a profound shift. It suggests the universe might just be, without needing a preceding cause or a starting edge in space-time. A truly self-contained origin described by quantum mechanics.
Wow. Okay, so we've covered a lot of ground, from bouncing universes to colliding brains and eternally inflating multiverse. And now this idea of a universe with no boundary, no edge at its beginning.
It's quite a tour of the theoretical frontier.
We've looked at the big bounce, potentially driven by loop quantum gravity, Brane Cosmology with the ekpyrotic model is one example, eternal inflation and the multiverse, and the Hartle-Hawking no-boundary proposal.
Each one offering a unique and brilliant, really, attempt to look beyond that wall of the initial singularity predicted by classical general relativity.
Trying to figure out what, if anything, came before our cosmic dawn.
And what's so compelling, I think, is that while these ideas sound like science fiction sometimes,
They definitely stretch the imagination.
they are rooted in serious, mathematically rigorous physics. They come from string theory, M theory, quantum gravity research. These aren't just philosophical musings. They're active areas of theoretical investigation.
People are writing equations, making calculations.
Absolutely. And ultimately, getting a definitive answer to what was before the Big Bang, if there even was a before, will likely require that holy grail we mentioned.
Quantum gravity.
A complete, confirmed theory of quantum gravity. One that successfully merges Einstein's theory of the very large, general relativity, with the physics of the very small, quantum mechanics.
That's the theory needed to describe the universe right at that initial moment without breaking down.
Precisely. And many of these models we've discussed are attempts towards that unification. They often make subtle predictions, perhaps about the CMB or gravitational waves.
Predictions that might eventually be testable.
That's the hope. Future observations, more precise measurements, might one day give us clues to favor one idea over another, or perhaps rule some out entirely.
But until we get that grand unified theory and the observations to test it,
The question remains open.
this question of a time before time, or a beginning without a boundary, it's going to continue to inspire and challenge physicists, philosophers, all of us.
It reminds us that our cosmic story, as incredibly vast and amazing as it is, might just have a preface. A whole chapter 0 that we're only just beginning to figure out how to read.
It's humbling, really, to think how much we still don't know and how much more there might be to discover about the very beginning and maybe about other universes entirely.
And that leads to a final thought, maybe something for you, the listener, to mull over. If any of these ideas turn out to be right, if our universe is just one bubble among countless others in a multiverse,
Or just one cycle in an eternal bounce.
or if its beginning wasn't an edge, but just a smooth point where time behaved differently, does that change how you think about our existence? Does it alter your perspective on the uniqueness, the significance of this universe, of humanity, within the grand cosmic scheme?
What does it mean for your understanding of the beginning if the beginning itself might not be a fixed, singular event, but something much more dynamic, maybe cyclical, maybe even a concept that dissolves under quantum scrutiny?
It's a profound question, touching on physics, philosophy, and perhaps even our sense of place in the cosmos, something to think about.